Okay, thank you. Hello everyone, good afternoon. My name is Alishba Ali and my group members are Shazib Ali Adil and Abu Huraira. Dr. Imran Khan is our advisor and Dr. Rashid Ali is our co-advisor, and the topic of our project is synthesis and characterization of silver nanoparticles. Next slide, please. To recap summary of our project, our goal was to synthesize silver nanoparticles by a novel technique using DC magnetron sputtering. The problem in already existing technique are that some of these methods produces unstable silver particles, some produces particles having greater size than nano range, and the others distribution is not good and uniform. To reduce the demerits of already existing methods, we came up with the idea of producing them through a novel technique involving DC magnetron sputtering machine. Next slide. We can produce these particles through two techniques. Our first approach was to sputter silver particles on glass slide and then remove the glass slide by dissolving in HF and then separate the nanoparticles from the remaining glass slide by keeping agent. Our second approach was to sputter silver target on 1 ml oil poured in cylindrical glass petri dish. Next slide. In our literature review, we found out that while silver nanoparticles they have attracted the increasing interest, that is due to their unique physical, chemical, and biological properties compared to their macro scale counterparts. When silver exists in their nanometer size scale, its antimicrobial properties they are amplified because of much larger surface to volume ratio and their small size. Like mentioned in the slides, the silver nanoparticles they have distinctive physiochemical properties including high electrical and thermal conductivity, surface enhanced Raman scattering, chemical stability, catalytic activity, and non-linear optical behavior. The other techniques used for the synthesis of silver nanoparticles, they have certain demerits as discussed earlier. So that's why we investigated the DC magnetron sputtering technique. The above mentioned properties, they are used in the following applications of silver nanoparticles. These nanoparticles, they are widely used for medical applications such as drug delivery and coating of medical tools. Another very interesting application is surface enhanced Raman scattering, which is used to detect cancer. Now I would like to call Shazib to tell you more about our project.
Assalamu alaikum everyone. Am I audible?
Yes, please.
So now I will be telling you why we did what we did. Firstly, we chose DC magnetron sputtering rather than any other technique because it is used for fabrication of nanofilms. It is a simple technique which gives us very good control over size and shape. And as you can see from this histogram that which we found from the literature that the average diameter is high between 5 and 6 nanometers. Moving on, after sputtering, what we did was dissolve the glass slide in hydrofluoric acid to separate the silver nanoparticle from the glass slide. But there was still some glass residue left. So to separate the residue from the nanoparticles, we needed to use a capping agent. Now the choice of the capping agent is very important because the capping agent actually influences various properties of the nanoparticles. And according to the literature, the best capping agents are listed PEG, EDTA, PVP, and PVA, polyvinyl alcohol. And the effects of these capping agents are shown here in the diagram, the antibacterial effects. And as you can see from this diagram, PVA or polyvinyl alcohol shows the best results. And fortunately for us, it was available in our lab, so we used it. Now, after doing this, after doing even more research, we came up with another approach to form these silver nanoparticles, which is potentially even better than the current DC magnetron sputtering one. In this method, we have to sputter the silver particles directly onto a liquid. But traditionally, the issue that comes with sputtering onto a liquid is that the liquid cannot sustain the vacuum or low pressure. But according to our research and the research paper mentioned on the slide, low vapor pressure liquid can actually sustain the vacuum. And among these low vapor pressure liquids, castor oil is our best option. And according to this paper again, the researchers did a TEM analysis after sputtering onto castor oil, and we can see that again the mean diameter of the particles is less than 10 nanometers, which shows great control, which we need. Moving on, here I will tell you about the progress we have made so far.
Sir Muzammil, am I audible?
Yes, please.
Okay, so I will tell you about our progress so far. We have done 5 experiments so far. In the first experiment, we did our first approach, which was to which was using DC magnetron sputtering and sputtering silver nanoparticles directly onto a glass slide. So we kept all the parameters constant, such as voltage, pressure, etc., but only changed one parameter, which was the deposition time. In our first experiment, the deposition time was kept around 10 seconds. And after performing AFM of the glass slide, it was shown that the average particle size was 200 nanometer almost, which you can see in the graph. And this is obviously not in the nano range, but as this was our first experiment, we let this one slide. We then etched the glass slide in a hydrofluoric acid solution, and then after separating the HF, after separating the glass residue by using capping agents, we performed UV test on the filter paper, which can show bright spots, which are silver nanoparticles on the filter paper. Next slide, Shazia. In the second experiment, we resorted to our alternate method, which was thermal sputtering directly on a low vapor pressure oil. As stated by Shazib, the best in this category was castor oil, according to literature. But our mistake in this was that we did not use pure castor oil, which resulted in a failure, and the equipment was not successful. And after this, we even consulted a company in Karachi, MSI, Material Sourcing International. But due to the current situation ongoing, we weren't able to successfully gather the oils in our limited time. In the third experiment, we sputtered the silver nanoparticles again, but this time, instead of 10 seconds, we changed the deposition time to 6 seconds. And this was successful, as our AFM resulted in 60 nanometer average particle size all the way down from 200 nanometers. Next slide. In experiment 4, we decided to go even a step further by reducing the time from 6 seconds to 3 seconds, which was a minimum time, because according to literature, 1 second is advised, but our equipment is not able to run only for 1 second and maintain a plasma. So in our fourth experiment, we decided to go a step further and reduce it to 3 seconds, which was successful, but it did not bring the size any lower and kept the average particle size at 75 nanometer. This shows the limitation of our device and shows that to achieve lower size nanoparticles, we'll have to change other parameters such as vapor pressure, even though we were already working at the maximum vapor pressure possible at the time. Next slide. In our final experiment, what we did was, after the glass slide was dissolved in HF, we did it again for our experiment 4 slide that we got. And then when the slide was etched in HF and we were left with a residue of glass and silver, we completely removed the glass by using vacuum filtration. And what we were left was with a pure suspension containing an HF solution with some water in it and silver nanoparticles. This was proven by our UV spectroscopy that we performed, which shows that silver particles were detected around 270 nanometer. The increase in the particle size is due to agglomeration that happened in the HF solution. And to prevent this, in our next experiment, finally we decide to use PVA, which according to literature is the best capping agent for silver nanoparticles, and reduce the size to 100 nanometer. Thank you. This is all from our side.
Thank you. Now questions from faculty members, please.
Ji, can you go back to your X-ray diffraction